Good morning. How's everybody doing this morning? Good. So, how Teranode enables unbounded scaling. Now, just to address the elephant in the room, I'm sure there's a lot of people wondering what's been happening with the Teranode project. And so I'm hoping to clear that up today with this presentation, but just to comment on it early, what we've ended up doing is iterating a little bit on the design. And in order to understand that, we need to go through the network and some definitions so we can understand what those differences are. So to start that off, I wanted to just quickly define the word unbounded, because a lot of people conflate unbounded with infinite. And they're two different concepts. So infinite is a theoretical concept that has to do with math. It makes math easier, whereas unbounded is having to do with reality. It's having to do with the resources that we have available. And in the context of Teranode, as more transactional activity is coming into the network, we're able to grow that bound. And so that's horizontally scalable, it's elastically scalable, and that's what we're talking about when we're talking about unbounded scaling. So the next topic, what is Bitcoin? And so if I were to ask you what Bitcoin is, if I were to ask you to explain it to somebody, just quick raise of hands, who would use the term cryptocurrency? Digital asset. Okay, so there's a few people. But the reason why I was asking that question is I just wanted to illustrate that a lot of people still think of Bitcoin and blockchain as strictly having to do with finance and payments and as a financial instrument. And that's not the case. So the white paper does define Bitcoin as a peer-to-peer electronic cash system. And today I want to expand that a little bit as we're talking about Teranode to an edge-to-edge electronic value system. And I say edge-to-edge because when we look at the network topology, what we want to do with Teranode is enable as much edge-to-edge communication as possible. We want to pull as much transactional activity to the edge of the network as we can. And we use the word value. I'm using the word value here because what Bitcoin is it's the first time we're actually able to give a discrete value to information itself, down to the packet. And that's a really powerful concept. And I want to tie that into some real-world examples. So this is Web3. When we're talking about Web3, we're talking about the web of value. And just to give you some real-world examples here, so we have streaming services, CBDCs, and data privacy. And dive into these really quickly. But streaming services, who's been seeing in the news lately everything about Netflix and how they're dealing with account sharing? So Netflix realized they're losing a lot of revenue due to account sharing, and so they've tried to mitigate that by bringing in some extra systems to stop it from happening. And one of the ways that they're doing that is they're trying to tie it to your IP, but then they've run into some issues with that. What if people are traveling? What if people want to watch it on their cell phone or their laptop? How do they account for that? It just adds all these layers of complexity because they're trying to fix the problem after the fact, on top of the root problem. So what if they were using blockchain? Well, if they were using blockchain, as we just talked about, they could charge per packet or per frame of video watched. And so this is why we need unbounded scaling, because 80% of network or of internet traffic is actually video streaming. And so if we want to charge by frame or by packet, think about how many transactions that is. It's a lot of transactions. We need unbounded scaling to be able to accommodate this. A couple of other great aspects of doing this. Users only have to pay for what they want, so it's beneficial for users. And also for Netflix, they can tie their user analytics into their financials. So you're kind of killing two birds with one stone there. It's a very advantageous way to reduce your infrastructure costs while also improving your user experience. Next example, CBDCs, and this is a hot topic right now. So central bank digital currencies. Now, there's a few options most central banks have been looking at when it comes to CBDCs. They either want to look at doing it in a traditional way, using databases, private databases, where they have to set up these private databases with the banks in the country and That entails a lot of extra infrastructure, and we all know how secure that type of infrastructure is. I mean, how many times have we heard about banks getting hacked or insurance companies getting hacked? I wouldn't personally want that system. The other thing they've been exploring are private blockchains. And so when I think of a private blockchain, that actually sounds a bit like an oxymoron to me, because you can't have a private blockchain. The way blockchain works, the way blockchain solves the double spending problem, is it publishes transactions to all the nodes of the network. And so there's only two ways you can solve the double spending problem. You either have to have a single entity that's checking all the transactions that are coming into the network, or you have to publish them all to all the nodes on the network so that if a double spend attempt comes in, all the nodes are able to reject it because they've already seen it. So, how do you do a CBDC? Well, there really is only one way to do a CBDC, and that's with a public blockchain. And right now, there's only one public blockchain that's capable of doing this, and that's BSV. And so the advantages that you get by doing this are interoperability, where you can have the digital pound, you can have the digital dollar and the digital yen, and you can have subnetworks or overlay networks. And we'll go into what overlay networks are in a little bit here, but using these overlay networks, you can have the central banks or the banks caring about their specific type of transaction or their CBDC type of transaction, and yet they can still interoperate because at the base layer, it's still a Bitcoin or BSV transaction. And so the other thing that I want to highlight with this is we learned a lesson through how the internet came about. So if we go back to the late 80s, early 90s, and we think about where the internet came from. Before the internet, we had what were called intranets, where you had a bunch of companies that were competing to basically build the internet, and they wanted to dominate that industry. But there were a whole host of problems with doing it that way. Interoperability being a main one, but also different upgrade cycles, different feature sets. And once a company got locked into an intranet, it was really difficult for them to switch over to another one. So just to reiterate, we need one global blockchain. The blockchain only works if there is one global blockchain, just like the internet. And to accommodate that, we need unbounded scaling. So just going into the last example here, data privacy. So another downside to how the internet works today is you have these large services, like I think Amazon Web Services or Google, Gmail, and they house all of this user data. So a user has to set up an account with these services, and then they have to trust those services to steward their data properly. And I don't know if anybody remembers the 2017 Equifax hack, where almost half the population of the United States had their personal information leaked, social security number, home address, phone number, etc. And that was used for identity theft, fraud, credit card fraud, all kinds of things. And so how would you improve that with a blockchain? Well, with a blockchain, since you're firewalling identity from the actual transactions, you can pull all of that information out into individual transactions that the user controls. So the user's only exposing exactly the amount of personal information needed for that transaction, and a hacker would have to attack every single transaction or even every single output in a transaction to get the same information. So it's not worth the hacker's time anymore. It's a disincentive. But again, think about the transactional activity that's required to make this happen. It's massive, absolutely massive. And so those are just 3 examples of Web3 applications of this technology. And I want to encourage you to start thinking about how you could apply it to your business or to your personal life. How could you start using this stuff today? And that sounds great, but it's also a lot of transactions to deal with, as we've been talking about. And just to put that into perspective, if we look at credit cards average about 5,000 transactions per second globally, with a theoretical peak of about 80,000. The Bank of England recently put out a request for proposals for the digital pound, where they stated the digital pound would require a minimum of 30,000 transactions per second, but could require up to 100,000 transactions per second. And that's just one country for a single use case. And remember, we're talking about value. We're not just talking about payment transactions. So with Teranode, we're running into the problem of how do we accommodate the millions of transactions that these different devices like IoT, industrial IoT devices are going to end up producing. And so this was our first attempt. And the next part of the presentation is going to get more into the technical side, so just to warn you guys about that. This was the first attempt we made at Teranode, where basically what we did is we took the components of the current SV node, and we pulled those out, and we put them into a pipeline configuration. And we tried to scale that out. And we had some great success with that. For example, the transaction would come in, as shown on the diagram here. It would go through the transaction validation pipeline, go into the mempool, and go into block assembly, et cetera, et cetera. But the problem we ran into with this is we realized that there were some components that were difficult to scale horizontally. Some of them had to be scaled vertically. And so that left us with a bit of a dilemma. We had to decide, do we push through with this design, even though we're not fully confident that we can get to the unbounded scaling? Or do we take a step back and rethink about it a little bit and take a new approach? And so we elected with the second option, and there's your answer for what we've been doing in the skunk works for the past couple of years. And so just to give you an idea of how we started thinking about this, this is how the network looks today. So SV node is a monolith. You have the small world network sitting at the center, and then you have the user nodes that are talking to those nodes on the edge of the network. And just to point out too, you don't see any lines between those user nodes because SPV isn't used very widely yet. But it's definitely a requirement if we want to get to the unbounded scaling. So we started thinking about how could we do this? And we came up with separating functions out. So going with a microservices architecture, a reactive architecture, because it's the right tool for the job. But instead of trying to pull everything out of SV node, how do we look at how a node works and those functions and creating separate services for each of those functions? So each of those services can be run by themselves or together, any sort of configuration that works for you. And now we have Teranode Unbounded. So just reiterating these points, the two main pillars of how we're getting this system to scale, and we know we need to scale because of the huge amount of transactions that will be coming into the network, are specialization and simplified payment verification, section 8 of the white paper. And so with specialization, if we think of a node is a network entity that is competing to add blocks to the chain. But further than that, it's successfully added a block to the chain in recent memory. And then we've come up with what's called a specialized node. And a specialized node is pulling some of the services or the functionalities out of that node, except for adding blocks to the chain. And so what this says is it allows specialization within the node itself. You can have an association of nodes. You can have a node as a large corporation that's setting services up in strategic areas or where there's resources available. It adds a lot more flexibility, and that's what aids in scalability. The other great part about designing it this way is it allows us to create these second layers. And so, again, this is part of how we're solving this problem. So we need to push or pull as much of the transactional activity to the edge of the network as we can. Overlay nodes is a great example of this. So if we go back to our CBDC example, this is how the Bank of England could do this. They would set up overlay nodes that only have a few of the functions, mainly the UTXO, transaction validation, propagation, and transaction storage. And then they would use those nodes to handle that specific transaction type, which would be a digital pound transaction. And then finally, we have the SPV wallet using Light Client and promoting the edge-to-edge communication of SPV. And so that allows us to grow the network in a distributed way, and it keeps all of that load distributed along with that growth. So moving into SPV. Why is SPV so important? Well, it's the same reason, but even more so, because of how transactions were designed, we have things like SIG hash flags, which allow us to do things like payment channels. This is Bitcoin BSV's superpower. Allowing edges to communicate directly with each other allows the network to scale unboundedly. This is really the key element. So we have this specialization, but SPV is really where the rubber hits the road. And so just to take you through an example of how this works, let's say Alice wants to buy coffee, and I'm Canadian, so she's going to Tim Hortons. So she walks into Tim Hortons, she walks up to the counter, Bob is there to take her order, and she orders a double-double. I realize that's a pound symbol, so this is a Tim Hortons in London. Bob gives her an invoice, which is kind of like a template for a transaction. Alice creates the transaction, and then she provides that to Bob, so this would be a digital pound transaction. She gives that to Bob along with all of the Merkle paths to the inputs of that transaction. Bob calculates the Merkle proofs for all of those inputs, and all he needs is the list of block headers to do that, and each block header is only 80 bytes, so it's very lightweight, very fast. And I'll go into how this actually works in a little bit more detail in the next slide. But once Bob is satisfied, so he calculates the Merkle proofs, and then he does a quick lookup to one of the overlay nodes to check that those UTXOs haven't been spent. Once he's done that, that pre-check is done, and he can give Alice the coffee and she can go. And then it's up to him to get that transaction submitted to the main network like a check in order to receive his money. And so you can see how doing it this way provides this off-network layer. It's this edge layer that provides the scaling. So just diving into this a little bit. How does this work? Well, the reason why this works is because of the way transactions are stored in blocks. So blocks use Merkle trees, which are binary trees, but it allows Alice to just provide those blue dots and the green dot to Bob, and then as long as Bob has the list of block headers, which only needs the orange dot, he can calculate the yellow dots all the way back up to the orange dot and do a quick comparison to know that that's a good input. And that's where zero comp comes in. So doing it this way is how we're achieving the unbounded scaling. Specialization and SPV. And if you think about it, by being able to do this, it allows us to see things a lot more clearly. And we can apply this to pretty much everything because information can be used to express pretty much everything. So if you can put a value on information, you can put a value on pretty much anything. And then you'll notice in the picture there, everything is going to the BSV node network, getting time-stamped, and so you have interoperability through pretty much anything you can imagine. And so I just wanted to leave one more thing before I open it up to some questions. But what really prompted me to get into this is every once in a while, there's an invention that comes along that really fundamentally changes how we do things. And to me, Bitcoin and Bitcoin SV is one of those times. That's one of these things. And so we're going to be running some pretty heavy tests soon. And We have some pretty exciting stuff coming down the pipeline soon. Calvin mentioned this in his opening remarks, that it's coming soon. And when he says soon, it means it's coming pretty fast. So I encourage you to go to that website, developers.bsvblockchain.org/Teranode, and sign up to get some updates on when this is going to be happening. But it is coming soon. TM. All right, so that's all I had to say for today. No numbers, unfortunately. We want to make sure that you can verify them if we share them. And I'll open the floor up to some questions.
Hi, Jake, great presentation. Thanks so much. When I was working on other projects with some boffins around scaling, like say the guy who designed Microsoft BizTalk, for example, or the kind of researchers in process calculus and whatnot, like all blockchains, in order to scale, need a mathematically provable conception of process calculus. And like one of the key things for me about Satoshi vision is like a Satoshi in BSV is a measure of the process calculus capabilities of the network to open and close an SPV channel, for example. I'm just wondering if any work has been done, because in other projects, say involving row calculus, they've mathematically proved that it can be scalable. They don't necessarily deliver as well as you guys, but there's that proof of concept that's quite powerful. I'm wondering if Craig or anyone has gone into that in any detail with respect to proving the unbounded scalability of BSV.
Yes, yeah, actually he has. He published a paper, I think it's around 2016 on that topic, where he proved that Bitcoin could be used for the base layer of the entire global commerce system.
Jake, great talk. I had a question about hardware for Teranode. So in terms of what someone like the Bank of England would need to be deployed, is the system that you're developing being created to use just like commodity computer hardware, or will they or will they need to purchase, some kind of specialized systems?
That's a good question, and something that we don't actually know yet at this stage. So right now we're testing it with commercial hardware, but if they wanted to get extra scalability, then maybe they want to invest in that. But it really probably comes down to use case.
Hey Jake, just a quick question on your graph. Do you see all those nodes that are non-edge as miners, or can they be non-miners as well?
Yeah, anything that's not in the center, those wouldn't be nodes. Yeah, the only miners are at the very center of the network, and likely there's never going to be any more than about 30 to 33 of them.
Thanks for a nice session. Regarding this Teranode, is it similar to sorting mechanism?
No. So it wouldn't be similar to sorting. The transactions are atomic and they're coming in, they're being validated, and everything is done reactively. So, yeah.
Thank you.
Hey, yeah, great talk. What is really exciting you about Teranode?
Oh, the fact that for the first time in history, we have the ability to put a value on information. That's just mind-blowing. What we can do with that, like I just showed you a few examples from Web3, but the implications of being able to do that are absolutely massive. And there's so many things that we haven't even thought of them yet. So that's what really gets me motivated, and the amount of good that that's going to do in the world, and what we'll be able to do with data privacy and access and key management, protecting people's information, etc.
Hi, so there's a lot of talk about writing to the chain, but I don't hear a lot of times people talking about reading from the chain. So if you're starting to put all this, validate all this data, and then later on somebody's going to access that and want to validate that, where do you see the reading part fitting into the diagram that you showed there? Would that be in one of those outside sectors, or where would that?
That's a good question. Yeah. So the main chain, its function is timestamping. And so you should never be reading from the main chain, and that's not a scalable way to design the network. So if you want to do a transaction lookup, you want to look at information, you want to store it on the blockchain directly, that'll likely come from a separate service using like a transaction storage service or an archive service. But it's probably more effective to use the specialization in a lower layer of the network, or SPV, where you're caring about your own information and then you're using the blockchain as an integrity check. So you're using that Merkle-proof process to ensure that the data hasn't changed, you have access to it, etc.
Hi, thanks for the talk. So please stop me if I got something wrong. So the big idea here is that you don't want to split the node up into microservices anymore, but you want to split it into this layered network?
No.
Like
so,
Bitcoin?
Yeah, we've split it up into microservices, but by doing that, that allows us to very easily create these next layers.
Okay. And the trickiest part to split into microservices and to have scale horizontally was the mempool, right?
I don't want to get too deep into the details, but there is no mempool anymore.
Okay. Yeah, that's what I was thinking, like, where is the mempool? So
Yeah.
there's no mempool anymore.
No more mempool.
But we have a different concept then.
Right.
All right. Looking forward to learn more about that.
Cheers, thanks.
If I can ask one more question tying into this. I learned yesterday from Dusan that there's multiple steps involved in mining. Like you can split it up to different steps. I think we were talking about 5 steps of mining a block. When you talk about specialization, are you talking about taking these steps to different nodes and then they can specialize on their service, bring it back to another node, and they're building it basically, the network is building the block together, or a group of nodes is building one block?
Very good question.
Group effort?
So it's not nodes trusting each other in that sense, but what you can do is you can create an association of companies who are running different functions of a single node, and they can come together and perform those functions of a node. So they can compete together to add blocks to the chain, for example.
Okay, thank you.
Great talk, Jake. Are you able to sort of enlighten us a little bit about how IPv6 fits into this model at all?
Yeah, for sure. So great question. Yeah. We're using IPv6 and specifically IPv6 multicast. And the reason why we're doing that is to reduce the network load. So the way multicast works is you send a single packet and then it gets duplicated when it gets as close to the edge of its delivery as possible. So that in itself reduces the network load.
I'm curious, you talked about this microservice architecture and some of the components there, how they're now being split up. Which of the, I'm just curious, how much of this were you able to sort of take from the SV node and how much of it is completely new, and like how much of it is still like C++? Like I know you can have different languages for these different components now and specialize everything, but how does the microservice architecture sort of, how much optimization, I guess, at various layers has occurred, and I'm just curious, like the prevalence of various programming languages in various, now that we can sort of specialize a little bit more, right, and distribute this across these different layers and services.
For sure, yeah, great question. So that's the great part about microservices, is it allows you to use whichever language is best for the job. We haven't done a lot of optimization yet. It's still early days. We're still testing this new way of doing things out, but I can confirm that we are past the other implementation already, which is nice. So we hit that milestone recently, and things are going well.
So just to clarify, when you talked about splitting up the functions amongst the nodes, Are you talking about where the nodes would share the fee, or are you talking about that certain nodes would just process certain types of data, certain types of transactions as a specialty, so to speak, or coming from certain sources? I mean, would that be like, one group of nodes gets this block and another group of one node gets this block and another that's specialized in one group, and then they have to wait, and then the next node
and then
is
they're
going to get the
kind of
next block
sharing-
and the next 10 minutes, or
sharing the work.
or are they going to be somehow sharing?
No, yeah. So another great question. So no, they still have to process all the transactions themselves. But what we mean by splitting them up is when a transaction comes into the network, say it goes to a transaction validation propagation service, and then it moves on to a block assembly service, that'll get split. It also gets stored into a transaction storage service, et cetera, et cetera. And so you can take those different components, and if you're a big corporation and you want to ensure that you're processing transactions very quickly, you can take your transaction validation and propagation service and put it next to a major internet junction point, for example. So it's more so, how does the node become more efficient? And then the other result of that is the second layer. So you can take those same services and you can create lower layers, and those lower layers would be interested in only a single transaction type, for example. But the main nodes are always dealing with all the transactions.
But then do you envision some sort of fee splitting amongst these different levels of functions and activities?
Yeah, that can happen for sure. Yeah, so if a node is using, or you have an association of companies and they're each performing a certain function, let's say each of them would be compensated according to the agreement that they've made together.
Would that be part of their protocol, or they have to sort that amongst themselves?
Well, they would sort it amongst themselves, but there's ways to do it with transactions. Transactions can have multiple outputs, so.
Okay. Thanks.
How is Teranode related to Chronicle, the last hard fork, which Shadows told us about 3 years back?
It's not really related.
Okay.
No more questions? Awesome. Thank you so much, everybody. Enjoy the rest of the conference.
Bitcoin mining, Bitcoin wallet, blockchain, stablecoins, MetaNet, the evolution of money. Everybody is talking about Bitcoin today, but what exactly is it? Learn the basics from experts. Learn what Bitcoin is, how it works, and why it matters. Blockchain 101, your ultimate guide to the fundamentals of blockchain.